So yeah, so this will be good. I'll put this on YouTube for you guys when we're done. Everyone's here, aren't they? $17. Yeah, I've got Lewis now. Yeah, I've got 17 of you here, so I can email in a second, say everyone's here. That's fine. That's fine. That's fine. So this is what we're moving on to. If I move that, that moves as well. Yay! So I can read it properly without turning my head. Engineering science to follow up engineering maths. Just fun. 4 learning outcomes, and this is going to be split looking at how I've done it in a similar way, but we might end up with more than 2 assignments because if we look at the criteria in a minute, we've got to do. So engineering science ties mechanical and electrical together, a little bit of materials and a little bit of almost the dimensional analysis we were looking at in maths actually, but quantitative and qualitative analysis of scientific data, which is all nice and fun. So SI units, which should be fairly straightforward, presenting practical data. So what I'm looking with the test procedures, etc., is just to skip to learn outcome 3. You've got destructive and non-destructing testers of materials. I would like us to do a destructive test of a material on our tensometer. Excuse me. To show how it breaks and the various stuff. If we do, that's why I'm saying we might have more assignment, because that will then become pretty much an assignment on its own, because it doesn't lend itself to being in with the other learning outcomes. 1 and 2 and 1 and 4 we can kind of tie together, but sort of 2 is mechanical, 4 is electrical, and then you've got this little bit of materials in the middle, which is slightly annoying me. Okay, so this is the content we've got to do. Nothing particularly that you shouldn't have done at level 3. But it's just making sure that everybody has done electrical and mechanical to level 3 for the level 4 course. Okay, so you guys are predominantly mechanical, so this stuff should be relatively known to you and just be a revisit of it. Again, we can get some experiments in with support reactions, fluids, fairly straightforward. 3 we've already mentioned. Structure of materials, metals, polymers and composites, material failure, and then DC theory and AC theory. Circuit theorems. So those who I taught level 3 last year will have done Kirchhoff's current and voltage laws, because I did it with you. We also did early circuit theories such as mesh analysis. These 3 theories are all pretty much of a muchness. They just involve calculating Thevenin involves calculating a supply voltage. Norton involves calculating a supply current. That's the basic difference. Okay. AC, and what we're looking at is what we call tuned circuits there, RLC. Then a little bit of electromagnetism. Because everybody loves electromagnetism, and we can't have transformers without electromagnetism. So this is why we have a slight problem. We could easily split into two. In fact, we had to put it effectively as two assignments in maths, because the distinction one was split across learning outcome 1 and learning outcome 2 in maths. In this, each learning outcome has its own distinction. So I could do it as 4 assignments if I wanted to. But I've looked at it and feel like this lends itself to being assignment 1, where we talk about SI units. Okay, we do an experiment to determine the support reactions of a beam, examine the quantitative data that we've established from the experiment, the qualitative data that we've determined from the maths. Okay, draw our conclusions based on the differences, okay, and get our analysis for the distinction. Does that bit make sense? So we're almost tying P3 into helping us complete P2, M1 and D1. Will's waiting to get let in. Yeah, he didn't beep at me. Oh, sorry, Will. Sorry, Will. It didn't beep at me to say you were waiting. Thank you for shouting at me. Yeah, sometimes I don't see it beep at me, so please point that. So does that make sense that this assignment will cover the first assignment will cover these 5 pass, 2 merit, 2 distinctions. P3 will form part of learning outcome 2, but the data you obtain from the practical that you do will then allow us to examine the quantitative and qualitative data. So quantitative values that we've got, qualitative values we work out. It's the simple way to put them. Archimedes principle in contextual engineering applications. I have a question on that I've written that people don't like at present. They say it's a little gruesome. It involves, could Rose have let Jack climb on the door with her and not die? And I'm being told it's a bit frivolous for an HNC. But that is basically Archimedes' principle in contextual engineering applications. So we're going to be working out the buoyancy of something, determining will it float, will it sink. D'Alembert's principle is going to come into our beam calculations again, and heat transfer on dimensions. I just need to check in this, and I've got a thing going. I've got a question written again. I've got it going in 2 dimensions, but I need to check whether they want us to do 3 dimensions. Okay, it's because it makes it slightly trickier if they want 3 dimensions. That's the only one. So that will be our first assignment, and I figure 3 to 4 weeks of teaching plus a couple of weeks of practicals to get that done. And if we write stuff up as we do it, I think you've worked my system out fairly quickly by now, that if you copy what I write on the board, it'll be in the assignment somewhere. Are you actually at work, Andy, or is that just a video of work? Well, I just thought you'd done like a speed. Did you know Speed didn't have a director? Yeah, the film Speed didn't have a director. Yeah, yeah, Keanu Reeves. Oh my God, there's a bomb on the bus, dude. Yeah. But yeah, Speed had no director. Do you know why? Because he's lonely. Probably better than you, Aaron. That's why you're not redoing it. Yeah, Speed had no director because if you add direction to Speed, it becomes velocity. Right. Yeah, this is where we have a slight. So, all things being perfect, this will be what our second assignment. Because these two are so different, whether to make it two shortish ones or one short one, where in essence that is one experiment and write up, where I just make sure that you answer those criteria in your discussion. Okay. And then this becomes an electrical one. Now this P9, we're basically going to copy what we did in maths, just, which is probably the one Will Godwin's going to ask me to go through. I think it was Will was asking about that one. Adding the waveforms together graphically, mathematically, and with the vector diagrams. So it comes back into the engineering science. Owen looks like he's going to want to ask that as well. No, it's nice teaching you lot that you can have your cameras on, because when I do this with the school, they've all got to have their cameras off. And you've just got this. I mean, Will and Lewis and Connor and that will remember from last year. It's like, some safeguarding, because we can see into their room. Yeah, basically. Either that or Thomas is really ugly. But because the kids didn't know how to put these backdrops in it, or we couldn't guarantee that they could blur the background, but it does mean you're teaching an hour to 2 hour lesson in front of a wall of initials who don't talk to you at all through the entire lesson. Yeah, and then we turned it off because you couldn't have your camera on. To be fair, Lewis was one of the better kids to have in the class, so I can't really disagree with that. But then it's like Derby County, one of the better teams in the championship. Still not really good. Yeah, it's like winning the one-legged sprint. You might have won the race, but you've still only got one leg. I better not say things like that. Actually, I'm recording this. Andy Brown is now eating a banana in my class. Right. So, my plan was to have this as one assignment, but I think it's going to be two shorter ones. So 4 is going to become a series of questions on electrical theory, and 3 is going to be effectively an experiment to show elastic hysteresis. See, thing is, then it talks about this is why I keep getting torn. So then it talks about electromagnetic hysteresis, which ties itself into M4. So that is probably on the morning of when you get the assignment, you'll find out whether that's one assignment or 2 assignments. Because I keep making my mind up, then rereading the criteria and changing my mind. If it's 1 or 2, you'll have the same length of time to do everything as you would. So it's not going to impact you guys at all. But it just one of those where you keep looking at wording thinking that'd go really well together, but it doesn't. Okay. So there's not huge amounts in the essential content, but some aspects of it are deeper than, for instance, when you look at Archimedes' principle and hydrostatics, 1, 2, 3, 4 words encompasses about 6,000 years worth of learning, testing and research. It's how they built the pyramids. So how deep do they want me to go with Archimedes' principle? No, they didn't. No, they didn't. No. You want a fact? What's this video? What? In what coordinate measurement system? What? So Cartesian coordinate measurement system. So something that hadn't been invented when the Egyptians using a base 16 counting system, or a base 10, or a base 8. It's not impossible. It's dead easy. No scaffold. Well, very little scaffolding needed. Using Archimedes' principle. Picking them blocks up would be very hard. However, what happens... Have I got any water? I've got some water. Right, okay, I'm going to bring my camera back. We're going to go completely off topic for a second. Although we're talking about Archimedes' principle. Can you see me? Yes, good. Right, it's going to pour... This is murky water because it's my painting water. I can pour my water into my glass thing. Okay. And I am going to find something that floats, which is, let's put in, I don't want to waste a mint really, but looking at it, that might be the only thing I've got. Right, my mint is floating in that water. Damn it, just give me a second. Turn that off. Come on, turn off. Right, my mint. Where are we? Is floating in that water. Pink water on the piece of paper, mint floating. See how easy it is for me to move that mint through the water? Why is it easy for me to move that mint through that water? Only for about 8 months of the year. What happened in Egypt, which is why they built Cairo where it is? What happened at that point of the Nile every year, which is why that part of the Nile, oh dear God, was so populous compared to the rest of Egypt. The Nile Delta flooded. What happened to all the slaves who were working in the fields when the fields were flooded? No, they started building pyramids. So what they did was cut the rock in the water of the Nile Delta, kept them cool. Water gives you a nice flat level for the top surfaces of your rocks. They then strapped shit tons of reeds to the rocks, because reeds are really, really buoyant. And they made the rock float just like my sweetie did. When something floats, where does it float? Top surface, on the surface of the water, yeah? So if you raise the surface of the water in an enclosed tube, whatever floats all the way up to the top of the tube of its own accord. Yeah, yeah. And if you look at the pyramid, you can still see it. You can still see it on some of them anyway. Aliens is a bit more realistic than using the theory of buoyancy they'd known about for about 2,000 years at this point. Look. So there's an old video on it. Let me find the right one. It's about 40 minutes long, I think. No, that's the 2-minute one. That's a 2-minute one. Here we go, 20-minute one, that's the one. Watch that. We're going to have to watch it anyway because it's going to be part of our Archimedes principle video. Hello. Alright, I've better since I saw you. I'm teaching a lesson here though, so bugger off. Yeah, I've got no symptoms, I'm fine. Will do. So that video, well worth. It will change all your theory that aliens built the pyramids. Let's put it like that. Okay. Sensible and latent heat, and then heat transfer due to temperature change and the thermodynamic process equations. That one's going to be fun. For continuity of volume and mass flow, I wouldn't mind doing Bernoulli's experiments, but that does involve filling up an enormously big tub of water and pumping water through a pipe. It's a good experiment. And again, what I'd like to do with this is get as much of this practical as we can. So you've got experiment data that you're then going against theoretical data, because that will tick. Let's share this again. That will tick this D1 really nicely if we can get 2 or 3 experiments to do it with. Okay, so that's what we're moving on to, science. Not huge amounts of stuff, but we'll go through it and make sure that everything's covered. I might do AC and DC electronics first to give you a bit of a break, and give me a break and give me a chance to teach some electronics to you. But the OCD in me might do 1 and 2 first, because 1 and 2 are first. Okay, so that is that. So if we look at what we were doing, it says assignment 2 version 3. This is where I'm looking. Everyone seems to be muted all of a sudden, unless you're all just listening to me. Excellent, that's fine. It's novel for a group to be listening and not talking to themselves, to be honest. Do I just? I know Lewis is the worst, isn't he? So if we look at this, what I would say in the couple I've marked so far, make sure when you're going through the questions, all of these criteria are covered somewhere in the tasks you've got to do. Okay. So, what we've got, it means I've been generous as far as I can with it being the first assignment, but make sure you're looking at these criteria when you're answering the tasks and trying to, in your head, link, right, for instance, exponential, yeah, where they cover in here. So model the combination of sine waves graphically and analyze the variation in results between graphical and analytical methods. Where might that be in task 1, for instance? Yeah. If you're doing that check on there, then chances are it will be in there once it's handed in. Okay, make sure you hand in all the work, Mr. Brown. So, going through this, task 1, adding waveforms together. Compound angled formula. Sine A plus B, cos A plus B. Did he storm off having a huff because I just pointed him out, or was he not? Did you storm off to have a huff then, or? I said make sure that you put all the work in when you hand it in, Mr. Brown. I know you did, but that is not an official submission, Mr. Brown. So, again, with it being the first one, I've let you off. Yep. Right. So this dog just wanders across Jack's screen every night. No, who was it? Thomas's screen. So, compound angle formula to add them together. Everyone okay with that bit? Yeah. No, this is the one that you're doing. I'm just making sure before I let you all go off and get on with it. If there's anything where a couple of people identify now, right, I want to go through that, I'll say, right, I'm going to go through that first. And if you don't want to listen to this, get off and do your own thing. and then come back if you've got problems. But what I don't really want is to go, right, go off and do your own thing, and then at, let's say, 2 o'clock, Lewis comes in saying, can you help me with part 2 of task 1? And I've just finished doing that, and then Will comes in and says, can you help me with part 2 of task 1? Part 1 is the bit I've just talked about. And you went, okay. We all saw you, Will. You and your mech warrior. What is that in your pen? So, compound angle formula. To simplify and add the waveforms together. Produce a single complex waveform and sketch that waveform over a single period. What most of you are going to do, I know, is combine the second part of that with part 3, where you are using a computer-based package to graphically model those two waveforms and analyze the difference or similarity between your graphical and Excel's graphical, or your graph and Excel's graph. Okay. The bit I think has foxed a few people is the vector form. So part 1, part 3 I think were fairly okay. Few questions come on the vector form. So is everyone okay with getting the vector form of y1 and y2? Or would anyone like me to go through that again? No. Is the nod yes, you'd like me to go through it, Will, or you're okay with it? I will go through that again. Okay. Sketching the waveform. Yeah, can do that as well. Yeah, so the scale drawing of the vector form it's actually worded quite badly reading that again. What we should find with a scale drawing is it verifies our addition of the waveform. So part 1, let's start, let's share this screen with you. There's a couple of, there's a great big watermark on it because I'm not on a smart board, but we can cope. So let's share this. In fact, I'll share that screen this time. Then I can pull things in and out. Right, so I've got here, this is my sheet, this is what I'm going to model. What I'm going to say is I've got two waveforms that are similar to yours. Y1 is equal to 8 sine omega t. Oh, so I'll give you an omega. I'm going to say 2 pi t for that, just to make my life a little easier. 8 sine 2 pi t plus pi over 2. And y2 is equal to 6 cos 2 pi t minus pi over 4. So 2 pi t basically means my frequency is 1 Hz because there are 2 pi radian in 1 second. That's why I've picked 2 pi. What you need to do is that your frequency is, let me get this right, omega divided by 2 pi, and so our periodic time is going to be 1 over that. So in essence we're doing 2 pi divided by omega. This is omega. Okay, so from that I can see that one period for me is going to equal 1 second. So when I'm doing my sketch, and I'll talk about the sketch, I need to be plotting this from 0 to 1 second, minimum really of 12 points. Sine wave like 12 points. You probably get away with 0.1 steps, but that could be why a few graphs I've seen a slight kink in them. So okay, but I would do 0.05 for mine, 0.1 and so on. Okay. So adding these together, doing the maths, we're going to get a waveform. And again, I'm just going to grab a blank Excel workbook. Come in here. So I know I'm going from 0.05. I'm just doing this quickly. Down to 1. So just by putting that extra 0.05 in there, I've now got 20 points. So this should be really good. Equals 8 times sine of 2 times pi times t plus pi divided by 2. And equals 6, was it? Just me to cover it up. 6 cos 2 pi times t minus pi over 4. Oop. 6 times cos. So those are the two waveforms themselves. Adding them together will give us this waveform here. Okay, and from this waveform we'll work out, for instance, go up to 1 in 0.1 steps, show minor grid lines, show major grid lines. So we can work out 1 second is 360 degrees, and we are effectively there. This point here should be here. Okay, so we're leading by 0.2 of a second. near enough looking at this. 0.2 of a second. So bring up a calculator. Okay. 0.2 seconds divided by the 1 second, funnily enough, is 0.2. Multiplied by 360 degrees, 72 degrees. Looking at the vertical axis, we go up to 13 at that peak, so our amplitude is 13. Okay, so this is why we've got this sketch, to get that 13 and the 72 degrees that we've got there. Okay, if you think 2.5 is going to be 90 degrees, so that's looking reasonable. Okay, so I've got as my answer, coming back into this one, write it in red, having sketched it, y1 plus y2 being equal to 13 volts times the sine of 2 pi t, and in this case we were leading, plus what's 72, let's keep it in radian, so it's, bring back my calculator, so rather than 72 degrees, let's multiply that by 360, nope, let's not do that, 72 divided by 360, there's our 0.2, multiply that by 2 pi instead to take it into radian, and we are 1.26 radian. Okay, I'm just going to remind ourselves of that 72 degrees. Okay, our addition is going to have as a sine and a cos in it. Okay, we know that it's going to be a certain sine wave plus a certain cosine wave. It's what we call a complex wave. But that's where we're at right now. So we've added them together using our complex compound angle formula. Literally put that compound angle formula as an equation into Excel and told it to draw it over the range of time that we've worked out the periodic time of our system is, and we'll get the one period of our compound waveform. While I'm on Excel, task 3, that is basically task 3, what I've done there, the start of it. Plot y1, plot y2, and plot them added together. And then overlay on that plot this sketch you've done in task 1. And show that the two waves perfectly overlay each other. The reason I've taken it back into getting what the amplitude and the phase angle is because of part 2. Because in part 2, what we're going to do is go onto a new page. New page. It's been a while since I've used Smart Notepad. And I'm going to remember that I've got 8 volts at an angle of plus pi over 2, and I've got 6 volts at an angle of, I'm just going to put a little c in there, just remember it's a cosine of minus pi over 4. This is not official notation here. This is just me reminding myself, and this is my sort of little sketches to do it. So pi over 2 radian. There are 2 pi radian in 360 degrees, so pi is equal to 180 degrees, so pi over 2 is equal to 90 degrees. Pi over 4 must therefore be equal to 45 degrees. Okay. But we have the added problem in a minute that this is a cosine wave, which we'll talk about in a moment. So what we're going to do is get a rule, and we're going to get a protractor. And I'm going to make my protractor smaller, just for now. I can make it bigger again in a minute. I just want it out of the way. Right, by a scale drawing, it means if your page is this big, make your scale suitably big. If your page is smaller, make your scale smaller. Okay. I can also have the advantage that I can make my rule bigger. So I'm going to make a 10 centimeter rule, but make it big like this. By scale, I mean if it is 8 volts, we draw a line 8 centimeters long. However, if your page is big enough, draw it 16 centimeters long. But everything then is doubled. So if you measure 20 centimeters for your answer, which we're coming on to in a minute, you've got 10 volts. In our example, we're aiming for 13 volts at 72 degrees. That's what we've already established is the sine wave of this complex waveform. Okay, so I've got 8 volts at a phase shift of pi over 2, 90 degrees. We always draw everything in relation to horizontal pointing to the right. So horizontal pointing to the right is 0 degrees. Kind of expected that to turn back to a pen for me. 0 degrees. Okay. So, taking my rule. We take our rule and we take our protractor. We put our protractor at a starting point on our horizontal reference. I'm going to make my protractor nice and big for you again. Okay. And we're going to measure the phase angle of the first voltage. I've coloured it red on there because I'm going to draw the line in red. But we get our pen. Make it red, and I'm going to mark where 90 degrees is. Move the protractor out of the way. You'll see I also have an added advantage on this, that my rule has a protractor at the bottom there for 90 degrees. You'll see what the slight problem I've made there. Which is easily solved. Oh. Did you know if you press Control and move something, it copies it in this software? I didn't know that. Okay, so now we're going to get our pen red because it's my red voltage up here, and I'm going to draw a line 8 centimeters long. at 90 degrees, pi over 2, to my origin, to 0 degrees. That is y1. And it is 8 volts in magnitude. Amplitude of 8 volts. I'm then going to take my second voltage. That's at 45 degrees, but it's a cosine. Going from this 0 horizontal, these must be sine waves. So we need to convert cosine to sine. So cos theta is equal to sine theta plus 90 or minus 90. Plus 90. I'm going to write it in. I'm going to trust my bravery, and I'm now just going to pop on Google and just quote that. Cos theta yes, it's plus 90 because cos of 0 is 1. There we go. Right, so we have to be at 90 degrees to start with, which my rule is, before we then take off the minus 45 degrees. So normally what we'd do is, so I'm just trying to find, there's a way to do it. It's like that. If we were just to sine minus 45, we'd have our protractor that way up, and we'd measure 45 degrees from that horizontal. Bob's a good one. But we're cos minus 45. So we need to add the 90 degrees on to our 0. Put our centre point at the end of y1, because we're going to do a parallelogram of forces here, basically, parallelogram of voltages, and we're going to measure 45 degrees down from the horizontal. In fact, better way to do it, set the 90 degree on the line, but put your protractor that way up. That's a better way to do it. Protractor up. Put this one in black, because it's my black voltage. 45 degrees down. I'm going to make a mark there, and I'm going to aim to go through the centre of that mark once I've got my rule there. Protractor out the way for a second, rule in, and again you should see that the angle measure on my rule, start the rule on the end of the red voltage, make sure your 0 is on the end of the red voltage, swing the rule down to the point you've indicated on there, and again Draw your straight line. £6 minus 45. This isn't looking good for my compound angle formula. Yeah.
When you showed me how to do mine, the cos line was up from the red. I don't know if that was correct or not. So
I'm thinking it should be as well. I think I've done something. Oh, cause yes, because yeah. Thanks a lot, Lewis. Yeah. So cos is sine of theta minus 90. So yeah, I've just missed a bit here. Thanks, Lewis. So cos 2 pi t minus 45 to bring the angle in is the same as cos 2 pi t, same as I'd use this more often in my lessons if I didn't have that bloody great watermark. Sine 2 pi t plus 90 minus 45. That's why it goes up for you, Lewis, because what we're ultimately looking for is sine 2 pi t plus 45. Easily rectified. Grab that, flip vertically. That looks a bit happier as well with what we're expecting. So I think you could tell we're expecting 13. I was looking at that distance thinking that distance is never going to be 13. Let me just check that distance there. 45 degrees. Oh, we're not quite 45 there. You see how there's a tolerance to 45 degrees on this rule. That's what's going to cause some of your discussion. Let's just get that to 6. Okay, yeah, so that was a slight error I made. Is everyone clear? Because in essence, apart from the length of your lines, your angles are all the same. That's deliberately so I can look at these diagrams and get some semblance of whether they're right very quickly. So, I now take my rule. I join the end to end, to the starting point to the finishing point. This is called a parallelogram of forces. I'm going to do this in blue so you can see it. Just had a horrible thought of something. Yes, I've done all of this and it's not on the recording. Right, I've just changed the capture. So we're at this point. So you missed the initial bit on the recording, but just to whiz through that again, just for the video. 8 centimeters up from the horizontal 45 degrees, 6 centimeters at 45 degrees, and then we measure end to end, and that doesn't half look pretty close to 13 to me. Does that look pretty close to 13 to you guys? Blue pen.
yes.
And if I get it right on my rule, I can normally get this to... For some reason it's not drawing along the rule. Okay, so I'm going to do it a different way. Put a line in. And we just make our line like that. Get blue. Put an arrow on the start. And you can see that that is 13 volts. By our measurement, 12.9 volts, I think, if we were getting desperate to be accurate with it. And we get our protractor. Measure the angle that blue line makes with the horizontal, making sure we start at the right point. 70 degrees by my eye on that. Let's get you out of the way. So graphically, y1 plus y2 is equal to 13 sine 2 pi t plus, what was it, 1 point some radian, 1.26 radian, which ties brilliantly back with what we sketched up from our original sketch. Okay. Then you've got your graphical method using the computer-based method. So this is a graphical method, and this is a simple graphical method because you're just drawing lines at angles. You've got the accurate Excel graphical method to say, look at this, they're exactly the same, or they're near enough the same that my eye can't determine any difference. Okay. But is it 70 degrees or is it 72 degrees, or is it slightly more than 72 degrees? And that's part of your analysis. So currently I went to point 2 on that. If we zoom in on this graph, we can get more and more accuracy. Yeah, say 0.2 is not bad on there. Okay, so what could have caused a 2 degree shift in my blue line? Yeah, the fact, well, I'm measuring 45 degrees here with a protractor, and the protractor's got a tolerance of error. Yeah, I'm then taking a rule between a point and a point and going, you know what, that's straight, but again, if you look at my protractor, that actually says 46 degrees now. That's 45 degrees. Or that's 45 degrees. So, you know, how long is 6 centimeters? Well, it depends how warm it is if you're using a steel rule. A centimetre is only a centimetre on a steel rule at 20 degrees. Any other temperature and it's stretched or it's shrunk. Okay. So those are some of the errors that are going. But this method is used to go, in essence, is my amplitude 13? Is my angle about 70 degrees? When you come into your Excel graph, you go, yes, my amplitude's about 13, 12.95 I reckon. And my phase shift is 0.2 seconds, which equates to 70 some degrees. I'm close. I'm near enough for the human eye to not be able to tell any difference between those two. Yeah. And again, some of you will get some comments like this. When we're checking, always hedge on you might still be wrong. So even if the two checks are showing that you're right, in your explanation, don't go, so I'm right. Say, two independent methods have given the same near enough value, so it implies that the calculation should be correct. Does that subtle difference in approach make sense as well? It's that almost a subtle difference as well of being, I did this against this was done. It's quite difficult to get your head around at first, but once you get practice, it's very good. It's not saying I'm right vociferously, but it's saying I'm right, but I'm not going to say I'm definitely right in case you find something wrong with it. Because if somebody else finds something wrong with it, you can always go and say, well, you know what, I looked on the balance of evidence and it looked okay. That's where you get to. Okay, so is that okay now for everyone? Yeah, so if there's nothing else you've got problems with. Yeah, so that's the idea. Okay, anything with task 2 while I'm going through the assignment? The last bit, okay. Any I think the differentiation one was actually fairly okay, especially once we changed part 3 to one you could actually do. Part 3 of task 3. Okay, so yeah, so in essence, you've got the velocity. Oh, in fact, have we done that? Oh shit. Well, that might be interesting when folk come back then. I'll run through who's left here right now. Everyone apart from Andy. I think Andy might have done it last year, which is Andy's still in. Let me just run through because it is really quick. Part 2 of task 3. Part 3 of task 3 is to plot dx dt in Excel and plot the integral that we're going to work out in Excel. Okay. And what effect changing Oh no, sorry, this is part 1. So plotting V for part 1, plotting displacement for part 1, which we have to do using Simpson's rule. Yeah, so that's the idea. So we've got that curve plotted in Excel already. Yeah, and then just change the value of that. Oh no, I'm going to have to change part 3 because we're not putting the angular frequency in anymore.
So have we done all the teaching then?
No, I thought we had, but we've not done part 2 of task 3. But it's really quick, so it's not going to take me long. But no, I've just read part 3, and because we changed part 1, did we change part 1? No, because part 1. No, you can still do it. It's all right. I'm being. I misread what C was. So it's a case of changing C in your graphs and seeing what it does to the time. Okay. So no, I'll talk about that in a minute though. So right, let's bring this on. New page. Part 2's dead straightforward. It's what we call a differential equation. Okay. So velocity. Let's go to black. Thickness. So velocity is equal to the rate of change of displacement with respect to time. We've established differentiation is the opposite of integration. If we differentiate something, we find the gradient. Well, velocity is the gradient of a displacement time graph. Integration finds the area under a graph. So integration finds us. So if we integrate velocity with respect to time, we get displacement. So let's say we've got an equation that says dx dt is equal to 5t plus 2t. Yeah, we'll stick with that. Okay. We can simplify that bit. Okay. So if you know what G is, you know what U is, we can simplify your equation. Does that make sense? In this case, becomes 7t.
Is G 0.81?
Yes. It should be gt squared over 2, but I didn't notice that until too late, and it'll still work as a question, so I didn't bother changing it. Okay. So this means that you need to calculate the displacement between 0 and 3 seconds. So this means you've got to do the definite integral between 0 and 3 of 7t dt. is equal to, by my reckoning, 7t squared over 2, or 3.5 t squared between 0 and 3. I've ignored the plus c because I know in this example that my c is going to be 0, because our displacement for a rocket starts at 0 meters at time equals 0. Okay, so completing my definite integral, 3.5 times 3 squared minus 3.5 times 0 squared is equal to 3.5 times 9 must be 27, 31.5, but let me just check that, given that I have a nice cool calculator app now. 3.5 times 3 squared (31.5). And we're after the displacement over the first 3 seconds, so it moves 31.5 meters in the first 3 seconds of its motion. Should have been slightly trickier than that because there was supposed to be a squared in there as well. But yeah, that's as easy as it gets. So you had to plot for part 3, let's drag this across. What we're looking at is, again, if we look carefully through our criteria, we're kind of tying M4 and D3 into this final bit, which is, okay, plot the velocity and displacement curves for part 1. Okay. So this is the velocity curve. The derivative of that, sorry, the integral of that is the displacement curve. Okay. You can get that displacement curve using the velocity curve and Simpson's rule. Okay. What we're looking at is plot this originally, which you're going to do to get part 1 done anyway, but then change the value of c in this equation 2 or 3 times up and down, overlay the plots on each other, and show what effect changing c has on the displacement of that graph. Okay. So you've got a value of c, so go like double it again, halve it again, and see if you get noticeable differences between those equations. Okay, again, let's just bring this up. My mouse isn't working because I've got my stylus on the pad. If I just bring you back in, just on that, so let's say, let's come down here, let's say my B and C So let's say my B is 10, my C is 4, then I'd be 2, I'd be 1, I'd be 8, and I'd be 16, something like that. Then I would be doing why am I looking at what's that exponential then? 40. I would be plotting equals 10 like that, 10 times e to the minus c times t times sine. Let me get this equation right. That's the wrong one. Times sine ct. One times sine c times t. So t is 0. How many? It's 0 to 2 seconds, wasn't it? It asks you to do it. My numbers might be massively out for 0 to 2 seconds. Why does it not like that? Because I've done the exponential of. Make sure you get your minus in the right place when you do the exponential. I need to put it inside the exponential, but then put that inside another bracket. Still not drawing it. My numbers are probably massively out for this. Let me just have a look at one of your data sets, which is possibly a bad idea.
Question number 8 is stated.
Whose was?
Number 8.
Number 8. 8 and 12. Let's have a look. Oh, wait, hang on. So 8C, 4, let me see. That would help as well. There we go, that's better. So I'd just not locked the equation, which is why it wasn't working. So again, I can see we're massively zero at 1, so I'm only going to do it up to 0.9. You can justify that by saying that. Okay, so that's your velocity. And you're going to take, now if I change that, say, to be 6, and I change it to be 3, can you see what it's doing to the velocity and to the displacement? That's become quite a good one. So that just completely inverts everything. Yeah, let's say 36. So you can just throw numbers in here. I wonder where it changes over. 24, 30, 12, 6. So what happens as I make C smaller? What happens if I make C 18? What's happening is the overshoot and the undershoot are getting bigger. Yeah, so our velocity swings up, down, and then settles. But if we make it 6, we've not got to the settle point yet in 1 second. It's actually going to take, looking at the numbers, it's going to take 1.7, 1.5 really, before we're anywhere near. If we go back to 12, can you see how we were at 0 around 0.7, 0.8? Go up to 24. We get to 0 about 0.4. It's quite difficult to see when you are only looking at one curve. Which is why I say, right, do it then. Let's say 6. Let's say 24. Copy that 8 across. I just want to lock the column on that one. So let's lock the column on that one. Let's lock the column on that one. So, lock the column on that one. I'll lock the column on this one. I'll copy that down. And then if I copy that across, what have you done? Why does it do that? Yeah. Right. Insert scatter graph. That definitely isn't showing series 1, 2 and 3. Oh, it is. Wait, hang on. IJ. So I'm being special. More like it. Okay. There we go. That's what I was expecting to see on the graph. Okay, so the effect of halving it, the red line, the effect of doubling it, the green line, and your values, the blue line. So in terms of displacement, it's travelled further and it's taken longer to settle. if we halve the angular frequency. If we halve the angular frequency, actually look at the blue, we're at 0.5, we're about 1. So halving the angular frequency doubles the length of time it takes and doubles the distance it moves pretty much. Looking at that curve, halving the angular frequency halves the length of time it takes to settle, near enough. Might even take it slightly further than half. So it's these curves I'm looking for that last bit. Yeah. And that can just be done plotting. Just plot the velocity. Don't worry about plotting the displacement curve, because as we know we can't get the displacement curve, but I wanted that to be a bit of a shock for part 1. Predict the effective change in the value of C. So from your curves you can then predict what the effect of quadrupling C would be. Yep. So just random points in the cell. My B is fixed. Multiplied by e to the minus c, which I've fixed to drag it down the column, multiplied by time, which is going to be 0 down to 2. And again, if you want to look at that and go, actually I'm only ever going to go to say 1 second, so I'll take it to 1, but I'll increase the points in there, feel free. This is you playing. Okay? Times the sine of CT. Yeah. Now what I've put the dollar in front of H42 for is to say then when I copied that equation across, it didn't change which column we were looking at for T. So it still allows the rows to change, to drag it down and work out each value, but it keeps the column the same. If we move to the next one along, you'll see what I had to do, because it was throwing a hissy fit at me, is I copied I40. In fact, it's still I40 in that first cell. I must have changed the wrong one. And you just got to make sure that you change the top one. I think I must have changed the second one down by mistake. Oh, that should be K. And that should be K. So all they're doing, just to pop it back to the numbers, yeah, that looks slightly happier. So while it looked like it was going massively negative, that's because Excel scales itself, which is why actually it's worth having the original waveform, the blue waveform, in there, because that's what our data was based on, and now we can draw our comparison. So quadrupling has basically flattened it pretty much instantaneously. 30. That would be pretty much what I would want. So this is almost critical control now. but all I'm after is we get this shape, and what happens to increasing and decreasing. So by predicting, you're going to take two or three, sorry, you're going to take 2 or 3 values and use them to set a prediction of, so this seems to be the rule, therefore it could be predicted that, yeah, if we divide it by 10, it will take 1/10 of the time to settle. Sorry, it takes 10 times as long to settle. However, then you could throw that one in. Yeah. So it's not a it's a level 4 analysis where I want data you've drawn to then predict what's going to happen. And the justification of your prediction comes from the evidence you show in your report. Does that make sense? Yeah. So yeah, sorry about that. I got confused when I saw C because I thought it was the constant of integration when I started that big for one off. But that is as easy as it looks, mainly because I forgot to put the squared in there. It's trickier when there's a squared in there, but it's and this one is drawing the graphs in Excel. Yeah, a logical analysis of a range of values to confirm what your prediction is talking about. From the data you've got here, so you analyze a range of values of C, and then make a prediction what effect changing C has on the velocity curve and therefore the displacement as well. So we know the displacement is the area under the curve. So if the velocity is taking half as long to settle, then basically the area under that curve is pretty much half of the area under the red curve. The larger the angular frequency, the faster it should take to settle. I believe. But you need data to be proving that. Okay, everyone happy with that? Blimey, it's nearly knock-off time anyway now. Yeah. Right. Only thing you need there is G. You've got a ball of light teaching you maths. Did I just look down and you got a glint off my head? Well, is that what you say? Cheeky fucker. I can say you weren't here, Will. So in the assignment it's something like that because what it's set is that G is a constant acceleration due to gravity. Now that might be different on a different planet. So in essence, you've got what U is. You know what G is, 9.81. So you're dividing G by 2. Then subtracting it from what your U is.
Would that not simplify to gt to the power minus 2, and then you integrate it out?
Nope, nope. Just G divided by 2 times T.
Oh, okay. Less complicated, isn't it?
You know, you're probably going to hate me for this. You know the integration by parts?
Yep.
I did kind of get it with lessons. Do you reckon you could like see
Yep.
through it and kind of just pick up little bits which I might have missed out?
Yeah, yeah. Tell you what. If I say that to that. What a lovely sight, Godwin. Right, okay, you should be able to share it now. If I stop sharing mine. Which if then we go into a breakout room. That was, oh God, who was that? George, wasn't it? I click a button and name disappears. I'm like, George Thomas, not George. So why unassigned? Room 1, assign. Okay, you're in room 1. I'm going to go into room 1, I believe. How do I do that?
It's not great, mate.
How do I join the room? Open. No, I don't want to add a room. I want to join a room. Join the room. Right, I'll be back in a minute, lads. Right, we should be on our own in here now, George. So you should now be able to share your thing so I can see it and...
Well, no, I've got it on paper, you see. I probably should have told you. I
Ah,
I've got it on my paper, you see, and I'm just going to copy it up.
right.
There's plans in it.
No, not necessarily. Hold it up to the camera, see if I can read it.
Could you just go over? Could you just skim over
Yeah,
the sort of technicalities of it, and then I can sort of pick up?
yeah. So, yeah, that's fine. So yeah, let's get back to my screen. So yeah, we're doing that one. So bring this back in, new sheet. So we're looking at V is equal to, let's say, 8e to the minus 4t sine 4t. Something like that is our problem, yeah? Oh. Have I put you on hold? Have I put him on hold or is he put him on hold? Well, this ain't working, is it? Says I'm on hold. I know. I'm trying to work out. Okay. Okay, so I go in here.
Is it not working, Andrew?
No, I can't remember how to work the breakout rooms. Close that.
Oh, the big yeah.
And now I think I've just killed George again. It said I was on hold for some reason in the breakout room. Okay, right, George, let's try this again.
You can just do it there if you want.
Yeah, probably is, because there'll be other folk not get it. So, right, can everyone see my screen? Rejoin the main meeting. I'm in the main meeting. Am I in the main meeting? Can you all see my screen?
I'll just take that off because all I see is Charlie now. Yeah, I was going to say.
Right, so everyone can see my screen. Right, so we're running integration by parts. So we're running the idea that the integral of u with respect to v is equal to v. No, it's not. The integral of u with respect to v is equal to u times v minus the integral of v with respect to u. So that's the formula we're going to use. And I've got a really cool. So that's the important formula. And folk wonder why I was so keen for the school to get smart note blooming boards rather than these bloody televisions. So what we have to do is work out what's what. So unless I'm completely mad, we just do u dv. However, because we've got an integral of v in there and we've got an exponential in there, it could be worth us doing it the other way round. So it could be worth us saying that they swap over. So that is my u and that is my dv. So I'm going to do one in green and one in red because we should end up with the same answer. Okay. But I think that way might be an easier way to do it. So I'm going to say u is equal to sine 4t I'm going to say dv is equal to 8 e to the minus 4t. So I've got u, I need v. Okay. So I need to integrate this term with respect to x. So this is coming as a... So the integral of 8 e to the minus 4t dt is equal to minus 8 over minus 4, or minus 8 over 4 e to the minus 4t. That's why using your e as the dv is often worth spotting, or minus 2 e to the minus 4t.
Why is it with respect to dt?
Because we're integrating it with respect to time. So our equation's got t in it, so we're integrating with respect to time. Okay. So if we carry that on, we've got u, v is equal to that. We've just worked it out. We just need du. Okay. So we need to differentiate u with respect to t as well. Differential of sine is cos I love the way it randomly picks at which point to cut. And multiply by 4, so we get 4 cos 4t. But we don't want du dt in our equation, we want du. So we need to take that one step further and say that du is equal to 4 cos 4t dt, just by taking that dt up from the bottom. So I'll rewrite all of those now down here. Oh, why have you changed my line size, you irritating software? So u is sine 4t. du is 4 cos 4t dt. dv I missed a bit off this, but it will make sense. dv is equal to 8 e to the minus 4t dt. I'll explain why I've added that dt on in a moment. So that means v is equal to minus 2 e to the minus 4t. So there are our 4 terms. This dt extra comes from the fact that our question is to integrate that function with respect to time. So we need to add that dt in to our dv. That then allows us to differentiate it as well, because if we have the dt there, that is then dv dt is equal to 8 e to the minus 4t, which is why integrating it with respect to time works. Plug this stuff in. Again, it's made my line thicker. So we get u, so sine 4t times v, so I've got minus 2 e to the minus 4t sine 4t u times v minus the integral of minus 2e to the minus 4t times 4, sorry, I did that in my head. I did that in my head as I was doing the sum, I'm sorry. Times 4 cos 4t dt, which simplifies down minus 2e to the minus 4t sine 4t minus the integral of minus 8e to the minus 4t cos 4t with respect to time. Now the problem now is that this is basically the same as the integral we've just done. The only difference is it's a cos. And it will always end up being, this repeating integral you've got to do. So this is as far as you take the maths. Okay, because what you say then at this point is this is a repeating infinite loop. So mathematically we will never be able to solve that loop, which is why you then use the trapezium rule which we did last week by plotting your graph in Excel, picking reasonable thicknesses of strips. I was watching George's face here and is it going in, mate? No, I didn't think it was. So the point of this task is that that sum will never be solved. So it's getting messy. So we do the one proof to show we can do the parts, but we then acknowledge that it's not going to go anywhere. And the key bit to task 3 part 1 is actually to draw to plot the equation in Excel and use Excel to work out, like the trapezium rule we did last week, the area under that curve. So it starts as an integration by parts question, but it becomes a trapezium rule question. It's your logical analysis then of the trapezium rule to say this is not going to be accurate, but it's going to be close enough for us, and it's the only way we can solve it. Alright? I think I've killed him. Yep.
You know, class 3.2.
Yep.
You know the answer that we get for that? Is it?
Yep.
Do you know whereabouts it's meant to be? 1 and 10. Like
Well, it won't be far because it don't travel very far.
yeah.
So it's not going to be in realms of.
0.9.
So where were we? Task 3. Which one are you?
Part done. Part
No,
three.
which student are you? So just equals. So I'm just. I'm just trying to incorporate.
Is that, I think I might know the thing. Is no that you showed us when you integrates like 70, I think you did. When it gets to the 70th square everything.
Yeah,
That over 2.
I'm getting values for the vast majority between 10 and 20. Well, there's a couple that leap higher than that, depending on how many random numbers have generated. What student number are you?
8.
4.95 if I've done my quick calculation properly.
I got 4.9275.
There you go, that sounds good to me.
Thank you.
Have you got your breath back yet, George?
Yeah, so I'm sure I'll figure it out.
It's say the just to tell you what, I'm going to stop recording this now because that's pretty much us anyway.